make sure that I'm speaking here to those online, so maybe now we are. So Energy Week is next week. There we go. But today we have pleasure to have a professor here from architecture, Michael Garrison, who is a wealth of knowledge about building energy efficiency and city planning and understanding the energy use of buildings and cities. So he has a long biography here. He's spent at UT many years. He's done a lot of things. He's the Cass Gilbert Centennial Teaching Fellowship in School of Architecture. He holds that position. He's focused on sustainable building design. He served as the UT Austin faculty advisor for many years of the Solar Decathlon, which is a Department of Energy competition to design buildings for net zero energy and low energy consumption and low carbon. So thank you for doing that, Michael. That's no small chore to help guide these teams who take a couple of years to develop these. He's published several papers that grants from the United States EPA, Department of Housing, Urban Development, Department of Interior. It's basically worked within the federal government and local governments. So if you are happy about building codes and standards here in Austin, he's very responsible for guiding some of that. So he's been the past chair of the Resource Management Commission, which is a commission that reports to the city council here in Austin, and chair of the UT Austin Faculty Building Advisory Committee, et cetera. So he has done many things. He has our wealth of knowledge about architecture and building energy consumption. So today he's going to talk about Austin meeting its climate change equity plan, relate this to some of the designs of the buildings and the Solar Decathlon. City of Austin has a goal to reach 50% reduction in carbon emissions by 2030 to achieve net zero carbon emissions by 2040. So buildings are a big part of that, not only because of the energy consumption in buildings, as he notes, but also because of travel to and from residences and our residential homes to our places of work. So he says we can do this and save some costs here at the bottom. So without saying any more, let's give a welcome to our own Michael Garrison.
Thank you. Thank you. It's a pleasure to be here, and thank you for coming on a beautiful day. Let's see, I can learn how to use this.
Yeah, clicking the screen first once, maybe sometimes just
Not advanced.
yeah. Let's see.
Okay, we'll just start.
I don't know. Quickly down for someone. Here you go here.
Okay. So to start with, I think you are. I'm just going to use this.
Yeah.
Okay. To start with, I think everyone's seen the IPCC, these graphs, that there's a 99% chance that man-made carbon emissions have led to our current condition of dangerous climate change. The IPCC says that at the current rate we're going, we're not going to make the Paris Climate Accord of keeping the temperature of the globe below 2 degrees centigrade rise by 2050. So that's bad news. We're not making progress. We're making great progress in the United States and in lots of the Western world, but a lot of developing countries are starting to industrialize. And so the actual amount of carbon that's being emitted into the air every year is increasing, not decreasing. And so we have these problems. We may not make it by 2050, 2 degrees centigrade, but probably, I think as Winston Churchill said, you can count on Americans to do the right thing after they've tried everything else. And so in that vein, we'll probably be looking at some more like maybe 3 degrees centigrade rise by 2050, or maybe a few years after that. before the problem gets so bad that we actually begin to do something about it. The implications of that, as you well know, are quite profound. So we're talking about by that time we would be beginning to see average temperature in Austin, Texas, which is about 96 degrees. In the summertime would be more like 110. And we would see the projection of some coastal flooding on some of our more beloved beach areas, Port Aransas.
Stop, go ahead. Okay.
Port Aransas, Galveston, these kinds of areas. So to compensate for that, the city of Austin has passed what they described as the climate equity plan. And the climate equity plan is, as you can see, looks for Austin to become a zero net emissions community by 2040. We're a very rich city. We're a very progressive city. We're a very green city, a very highly educated city. So if we can't lead the way, who can? So when we look at their chart, we can already see that we've made great progress. A lot of that had to do with COVID. So the average person in Austin is generating about 12.3 metric tons of carbon emissions per year. We can compare that to other locations. In Germany, that number is 9 and dropping. In France, it's 4. And for us to actually mitigate climate change, we would have to get that number down to about 2.5, which is basically what you find in most of the countries in East Africa. So those are daunting goals. And to make a change of this magnitude, we would need lots of numbers. You can't just have 1 or 2 green buildings, 1 or 2 zero net energy buildings. You need literally thousands, tens of thousands. In fact, in the Austin equity plan, climate change equity plan, we're looking at reducing the energy use of all buildings in Austin by 25% by the year 2030. That's 467,000 residences and over 51,000 buildings. Reduce their operational energy use by 25% by 2030. In addition to that, we're looking at reducing the energy use of new buildings by establishing a zero net energy code. We're going to have a zero net energy code in this city by 2030. All buildings must be zero net energy. Today, they must be zero net energy capable. And we'll look here in a minute, but the EPA is suggesting a new code that's zero net energy ready. And so what do those terms mean? Capable means you have to have a way to get to zero net energy. And so it's a very ambiguous term and it's not doing much good. Zero net energy ready is about a 55% reduction in energy from building code right now. So that would be the minimum standard that we need to hit for new buildings in the near future. But Austin, to be able to meet its ambitious goal, requires to build 100,000 new zero net energy housing between now and the end of this decade. That's a tremendously ambitious goal, considering we have about maybe 2 or 3 existing zero net energy buildings in Austin. So how do we do that? Well, if you can see on the graph on the left, that we made tremendous progress in Austin during the COVID years. We dropped from about 12.8 metric tons per person down to about 10.8, and now it's leveled off. That's because I think we've done most of what we consider to be picking the easy fruit. Energy conservation systems are now pretty much the norm. A typical building built today uses about a third of the energy per square foot that a building did in 1970. And that's primarily because of lighting technology increases. That's had to do with better envelope design and has to do with a better mechanical systems. So we're doing some good, but zero net energy is another goal altogether. Not only do we need to build 100,000 new zero net energy buildings between now and the end of this decade, 80% of them must be inside the urban boundaries of Austin to deal with the transportation load. Because if you can see in this chart on the transportation load, which is in orange here, I'm sorry, it's in burnt orange, but in orange here, you will see it's relatively flat. That's because most of the new growth in Austin has been in the suburban areas. We have two of the fastest growing suburban counties in the United States, and they tend to use more energy in transportation per capita than urban development. So we have to have these new buildings within the urban boundaries to be able to deal with the transportation load. In fact, by 2030, we're proposing that half of all trips that people take will be by public transportation. We'll have to ask who besides students are using public transportation, which includes people power, like bicycles or walking, which means that we have to have more mixed use urban development to be able to attack our transportation sector. Austin now has the dubious honor of having the highest per capita miles traveled per day in Texas. We're exceeding Houston or Dallas now, primarily because of our rapid suburban growth. Now, you can see in this chart, the line that's diverging towards the bottom is the new goal. You can see how rapid it requires this change to be made. The faint line that you see above it was a direct sort of like a constant line, which was trying to get us to being zero net energy by 2050. So we're looking at zero emissions by 2040, which is actually increasing that quite a bit. And that's trying to get the temperature at 1.5 degrees centigrade. So if everybody did that, we could get that down to 1.5 degrees centigrade. And as you can see, we're falling short. We're not keeping up with that pace. In fact, all the changes, all the good that we did during COVID, we're actually have increased our carbon emissions within the city a little bit because of transportation. So there are other ideas that we have to do. We have to reduce our refrigerant leakage. We have very small industrial a component here in Austin, but we're looking at those being reduced by about 25% to be able to do that. So that's the goal. That's a very ambitious goal. Some would say impossible goal, given where we are. So we have the technology, the good news, off the shelf right now to achieve those goals. We don't have to invent anything new. We just have to have the wherewithal to do it. The biggest thing to take away from that is to actually see where we're generating those carbon emissions here in Austin. It turns out 84% of it is basically a policy on where we build housing and how we build it. 84% of our carbon emissions come from the operational use of housing and the transportation use associated with that housing. So if it's suburban housing, which has more surface area than apartments, for instance, and we have, in terms of dwelling units, we have slightly more apartments than housing in Austin, but it's pretty close. And as I said, we have about 467,000 housing, and we're adding anywhere from about 20 to 40,000 new units a year. So how do we do this? How do we go after this goal? Well, to actually get the numbers, you have to address the three legs of sustainability. So one, zero net energy. Turns out that's the easiest one to do. Just using off-the-shelf technology, we can do that. It's making it affordable is the problem. Because if we don't make it affordable, we don't reach the moderate and affordable housing market, which is 2/3 of the market. So what we have to do now is move this from the luxury market, which you might see a few zero net energy buildings in the luxury market, into the affordable and moderate income housing market. And then we have to be able to make that compatible with existing neighborhoods so they will accept the number of multifamily units that we're proposing to be able to get to this zero net energy goal. Those are daunting tasks. So let's start with them. First of all, as I said, it's relatively easy, I think, to get to zero net energy. And the way you do that, of course, is to begin to use the new EPA and DOE zero code. And so we start with the energy code, the IECC, the International Energy Conservation Code. And that sets the minimum R values for our walls and ceilings. It sets infiltration load. It sets the minimum U value for windows, these kinds of things. And so that's code. To do Energy Star buildings, we're doing about, we're reducing that by about 45%. How? Well, we're increasing the level of insulation. The new 2021 code increases the insulation level required over the 2016. So instead of R11, we now have R13 walls. Instead of having R26, we have R38 ceilings, this kind of thing. So that's the first level. The second one is that we start making buildings much more airtight. Right now, we're looking at maybe 4 air changes an hour in a typical residential building. That's pretty shoddy construction. We've got to get that down to somewhere around at least 1 air change per hour. So we're going to build buildings more airtight. As we do that, we're going to have to meet the EPA new Air Plus standards for healthy interior environments, which generally means we're going to have to add energy recovery ventilators to our mechanical conditioning to be able to make sure we get adequate fresh air. Then after we do that, we're going to move to the next sphere, which is zero ready. EPA and DOE zero energy ready standards, which is about 55% below code, which means additional insulation, additional tightness in terms of infiltration. So now we're getting down to maybe 0.75 air changes per hour. And finally, what we're proposing is we use what's called Passive House, which is a German standard for energy conservation within a building frame. So that has to become the sort of norm. That's 75% below code. What does that mean? R34 walls, R54 ceilings, half an air change per hour. That means shading coefficients of 0.2. It means U values for windows of 0.25. So that's adding money to the cost of building. And in the moderate and affordable housing market, that's difficult to do. So we estimate that that's probably adding about $7 a square foot, passive standards, to the cost of construction. And when we're talking about moderate to affordable housing, we're talking about $150 to $200 a square foot. The luxury market starts at about $300 a square foot. So we're concentrating on that market. So we have to be able to absorb that cost. And we have to absorb that cost by cuts in other areas to be able to do that. And that's where we came in. So the first thing we looked at is prefabrication. Why are we building houses by hand, one by one, like we did 100 years ago? We're one of the last industries to actually industrialize, to be able to use some kind of prefabrication. So over the years, we started in 2000. This was our first solar decathlon house on the National Mall. We did this in conjunction with the Center for Maximum Potential Building Systems with 25th. And so we built it here in Austin. We took it apart and transported it to the mall and had it in operation for a week, and then took it down and brought it back to Austin where it still exists. So when we're looking at a project like this, we were not only zero net energy, we were trying to be annual water neutral. And we started looking at embodied carbon energy, which is not being considered right now by very many people. But I would tell you, by 2050, half of the energy that a building uses is in the embodied energy required to make the materials to build that building. So we have to address that within that. You started out by kind of trying to do something like a Kia does, which we have a sort of kit of parts, and that we would make these kit of parts and then we would assemble them on the mall through a series of, some assembly required. So we were looking at trying to get some things recycled. So we went and bought 6 recycled junk cars, basically, and took them to Seguin, Texas, had them made into light gauge steel. So there was some upzoning of that. There was some, upcycling of that. We also worked with the Airstream company to sort of like redo their Airstream. So we got an Airstream, completely gutted it, and rebuilt it from the inside out. That became our sort of kitchen and bathroom for the project. And we couldn't use a crane on the mall at the first competition. So we used the old Roman idea of a sort of block and tackle, where we were using these unistruts, if you will, to put together. And then we would use those to raise the roof up into it. So you can see the students doing that here. And so this is us on the mall. You can see the boxes that we would bring off the mall, off the truck, and then some assembly required. Yes, it took us like 4 days, day and night, working around the clock to get this thing together. And when we finished, more people came through that project in the week that we were there than attended the UT Oklahoma football game that year. And so it is really highly interested, the public's highly interested. In fact, the Solar Decathlon is the largest public relations event that the Department of Energy holds. That's now worldwide. But in this case, we were looking at a 3.5 kW system. We tried to limit it to make it affordable. What you see in those white boxes are the water tanks. So we have a gray water, we have a black water, and we have potable water. And we had I think the best imitation of an engineer by an architect in our system. We were using a small little fan coil unit using the hot water that we're getting off of these. I don't know if you can see this or not, but the evacuated tube hot water collectors, which were acting as a shading device over our kitchen and bathroom area. So we were great. We finished third in design in this competition, but there were problems. And this is talk about a tough jury. That's Glenn Merkitt, the Pritzker winning prize architect. That's Ed Mazzaria, Dr. Doug Balcom, the head of the Los Alamos Passive Solar Energy, Barry Jackson, the head of AI. So only the students, and we had pretty much a female team, were allowed to sort of like be in that review. And this is what I mean by this is the best imitation of an engineer by an architect. And one of the things that we discovered is two things. First of all, we had to get enough energy also to power an electric car to meet all of our needs of that. And we had to drive a certain amount of miles every day. And so when you can see over here on the right, that the energy being used by the electric car was way huge. That was our largest energy use. And we also employed an ice battery with our mechanical system within this to try to shift the load a little bit. And then we had fan coil units where we're sending hot and chilled water to each one of the rooms that we have within the space. What was wrong? The infiltration load was huge when you do a kilowatts. So we actually could never get the load low enough to be able to make it zero net energy. And so that was a learning curve. In 2005, we did it again. And this time we decided to do fewer pieces. So we're allowed now to use a crane on the mall to do this. So we worked with Oak Creek Homes in Fort Worth, which is doing modular housing, and began to understand sort of like how you do chunks, as we call them. And so this is all basically using SIPs, structural insulated panels, which were metal SIPs with a styrene core, a poly styrene core. And then we found that that doesn't meet 1 hour fire rating. So we had to put burring strips and then put 2 layers of gypsum board on the front side of that so that we could get the fire rating, because if there's a fire inside, the styrene would have melted. And so you would have lost structural integrity. So we're kind of learning what the module needs to be. This was put together in 4 chunks, each one of them 8.5 foot wide. So we brought them out to the mall and put them on a foundation frame because you can't penetrate the ground on the National Mall. It's sacred ground. So we had to invent a leveling foundation device. And we invented this, you can see it up on the upper left, using bowling ball technology, a way of taking these chunks off of the truck, putting it on the frames and rolling them into place and then snapping them together. So we call this the snap out. We pushed the roof up and that became the main space. You're seeing the bedroom wing here on the lower right. And by the way, that's redwood wood on the outside as the rain screen. But we didn't cut redwood trees down. That comes from a UT winery out in Fort Stockton that we went out and got the leftover redwood from their barrels and we framed that in the shop and used that. And then behind that, as the waterproofing layer, we went and got the Daily Texan aluminum sheets that they used to print the Daily Texan. I made those shingles that covered that. So we were trying to reuse materials wherever possible. And the exterior on this, we were experimenting with, we used with zinc. So that's the exterior of the building. The interior, we used mesquite, which is an underused resource here in Texas besides barbecue. There's 55 million acres of mesquite in Texas. So we were actually looking at using that type of system. And we won a number of awards on our project. We won the BP Solar Award and we won the Hot Water Award. And so you can see we're kind of experimenting with what new technology is. So this is bifacial solar collectors, which means you can the light will go right through them, so I can use them as shading devices. So that's our overhang. The evacuated tube hot water collectors, you see we made it a wall. So we made it sort of like at the entry wall, which you can see in the middle slide, where it doesn't have to sit up on the roof because we needed all the roof for photovoltaics. We began to find that, wow, to win the competition, you need a bigger engine. So 3.5 got replaced by 7.8 kW system within that. And so this was our system. We had the ERV. We had a small air source heat pump. And all of those were able to be run by the collectors. We reduced the infiltration load, yes, but not enough. Still those joints, just because you're building it one time and when you rebuild it again, we did all kinds of sealing, neoprene sealing and all those particular joints, but that's still a very, very difficult joint to make. While our performance was much better, we decided it just wasn't really good enough. So in 2007, we finally figured out that the way you do this is that you listen to the people at the modular home companies. And we decided that we realized that we were asking them to make too many changes. And so what we asked them to do now is to pretty much use their existing technology, the way that they build things. They build a house in a week, they finish it out in another week, which saves so much energy because normal house is built in 90 days. That means I'm saving construction financing costs. I'm have a higher quality of construction because it's being done in a factory instead of in the field. I have no rain days. Within that, I can buy in bulk, which all of that ended up meaning that we got about a 15% reduction in cost over existing site-built buildings. And so we only asked in our sort of manufacturing process, and we started working with Affordable and Palm Harbor Homes, which builds their buildings on a platform, a steel platform that they use as the way to transport the building. So we were able to get the cost way down. And now we're able to sort of like input these new costs, the new costs of passage house, the new R34 walls, R54, tighter construction, and built a what we decided was a more energy efficient modular home. So in 2007, we did that. This was out at Mueller. This was one of the old hangars out at Mueller. We use again sort of metal sits in this case, and in about 9 weeks, we put this whole thing together. And some of the students were learning welding because we had to make our own chassis to do that. In fact, one of the students that learned welding, after he finished, he started a furniture company, an outdoor furniture company in Los Angeles, which now employs 25 people and has sales of about 54 million a year. So we started seeing students getting spinoffs from some of the work that we were doing. So we put this house together over the summer, transported it up, and this is basically what it looks like. You can see the idea, though, of having an open interior, which we wanted to do, as opposed to what you see in a typical modular home. We had no shear strength in that. So we built moment frames. And a moment frame means that we have these steel frames that come along the outside of the building over the roof to give it its lateral stability and still allowing us to have this sort of open interior. So we got smart enough to start working with some engineers. And so we worked with the Arc Engineering, and Attila primarily was involved with us and really worked out the system with us. This is the interior of that project. And we were very concerned about using gypsum board when we started getting into Aera Plus. So this is all, we didn't tape and joint things. We ended up getting using some MDF, which looked better in terms of its off-gassing and in terms of its embodied energy. So these are some of the pictures of the interior. And when we were finished this project, we brought it back to Austin. And this is the interior of that. So we're using radiant heating within this. So we have what's called a warm board. So we have more hot water capacity in this particular building. This is primarily some suggestions from Attila that one board is running water in it at about 84 degrees Fahrenheit. We tried using it as for cooling, but at 66 degrees, we were below dew points. So we didn't do that anymore because we were getting condensation issues with that. We also needed a dump for the hot water that we were generating. And so that's what the hot tub on the deck ended up being. And so we, at the end of the life of this, we took this back out to West Texas. And it now exists at McDonald Observatory. So it's a facility that's open for the staff. And so this was, we were half arch engineering and half architecture students. And that, again, is our classic 7.8 kW system for that particular house. And it sits right below the telescopes out on Mount Long. And the airtightness of this and the energy efficiency of this, we were zero net energy just fine. So our last one, in 2015, we worked with Werner Lang from the Technical University of Munich. So we had a German Austin art in engineering team. We worked with some of the other people from mechanical engineering. We had a couple of PhD from students from mechanical engineering. And this was the building based on an old diagram, but primarily what we're starting to look at is embodied energy. And that's why you see the abundance of wood that's on the exterior of the structure. And so all of that wood to make it fire resistant is been soaked in some borite solutions for quite a bit of time. And so the building is really just a nuclear building. It has sort of bedrooms on one side, the living room and dining room on the other side, with an enclosed area that you can make as a sunroom, but it's a breezeway as a dog run right through the middle of the building. You can see this was the truck. This was the truck leaving East Campus, where we built the house, and arriving in California, where we did the Solar Decathlon competition in Orange County in that particular project. This is the project as it was finished in Orange County. And again, after we got the mechanical systems to sort of work, it ended up, hitting the zero net energy scale. That we really didn't have problems with that. One of the things that we saw with this was a sort of criticism is that we have more surface area because we have two houses instead of one. And we're doing that to enhance ventilation, which represents about 23% of the year here. So it's not like you're building in a northern climate where you want to minimize surface area. We want to sort of like have an energy efficient envelope, but we also wanted to take advantage of that 23% of the time when we could use outside air, outside ventilation to be able to solve that problem. So we have this large deck on the exterior of the building, and this large shaded one. We're capturing all the water for the building. And again, we're trying to use a whole series of reclaimed woods. That floor, for instance, was an old cotton mill in came from some beams from an old cotton mill in East Texas. So again, you see a dominance of wood within this particular project. And the other thing you have to do within the competition is cook a meal for the judges. And so, of course, we work with some local permaculture folks here in Austin, and began to sort of look at how can we incubate the garden using some of the water that we're trying to clean, where you end up with a cycle of having an aquaculture, where the plant are being fed by the aquaculture, and the plants cleaning the water for the fish. in that case. And so we had the tilapia fish and that we were serving them, and began to look at this. Can you make food security for affordable housing in that particular area? And this was the mechanical system. You see, we've moved away from solar hot water heating and now using heat pump technology. So instead of trying to find more heat to make the solar water heaters more efficient, the heat pump technology for a hot water heater, which I think is coming out of the Oak Ridge lab work, is just so much more energy efficient than any solar water heater systems that we could find. So we were also using a water battery, this case, instead of the ice battery. So that's what the tall column that you see on the left. So through these projects, we were able to sort of document that it's possible to use off-the-shelf technology for zero net energy. And we were using the reduction in building costs, again, that sort of 15% reduction in building costs, to absorb the extra costs of using passive house conservation systems. So we were saving about anywhere from about $17 to $20 a square foot. And we were increasing the cost of the building by, again, somewhere around $12 to $14 a square foot for the extra conservation system. But that doesn't get us to zero net energy, does it? I guess it's to zero net energy ready. So we had to put the PV panels on it, which cost us about $7 a square foot for a grid tied system. So when we finish all that out, we actually, through our energy savings from the conservation side of that, and our cost savings from the prefabrication, we're actually a little bit below market rate for these houses. So it's possible to do it. It's possible to make zero net energy below market rate, just using that kind of technology. And this is that project again. It's again out at McDonald Observatory. If you want it, it's on the tour. You can go see it. So that gave us to the next problem. So we can make it affordable, and we can make it zero net energy, but would the neighborhoods accept it? Is it compatible? And you know about the fights that we've had here in Austin about trying to put new middle density housing within existing neighborhoods that just don't want to see it because they believe that it is against the character of their neighborhood, the design character of their neighborhood that they've lived in all their lives. So we actually started working with the Blackline Neighborhood Association on the Solar Decathlon Challenge project, which is our fifth Solar Decathlon project. We don't build it on the Challenge project. We actually just simulate it. So in this case, we looked at we went to the neighborhood said, well, first of all, you need to respect us by looking at what we have, by looking at the character of what we have. So we began to look at the bungalow houses that were built within the Blackline neighborhood. These used to be Swedish farmers, which were these tall, narrow buildings. And then in 1927, during the Jim Crow laws, when people of color were forced to live in East Austin, they ended up being filled with these bungalows, with these porches, because before air conditioning, people would come out onto the porch after dinner to take advantage of the breezes. So they were very proud of their buildings, and we began to work with them, and we produced some sketches about density for them and setbacks and what's called the building tent. And we ended up working with them and coming up with some designs that they could live with, which were basically some row houses that were limited to 2 stories along the neighborhood streets, and then 3 stories behind those 2-story row houses. That was what they were able to live with, that they thought was compatible. So this helped us with the cost per unit. So instead of looking at a density of 1 unit per, looking at a density of something like around 7 units per acre, which is what single family detached is going to give you. we started looking at about 30 units per acre as a compromise. As you well know, the density that was being proposed by Codex and some of those were all the way up to around 60 units per acre, 45 to 60 units per acre. So we tried to work from the bottom up back to the city. What can the neighborhoods live with? And so these row house designs became something that they thought that maybe they could live with, that would maintain the character of the neighborhood, that would be more compatible and more socially equitable. So again, we looked at prefabricating these. So we were looking at basically 1,000 square foot and 1,200 square foot apartments, where 20% of them would be ADA available, and putting those onto the lot. We can see on the neighborhood streets, we have the 2-story row houses, and in the back there's a 3-story, and those are the accessory dwelling units that use that are ADA and have a roof deck on top of that, which are covered with PVs. So we ended up finding that because of the efficiency that we were working with, we were able to get our PV sizing system down to about 3.5 kW per unit. And because we now have 14 units sharing the land that used to be occupied by 2 houses, we're making it more affordable in terms of the land cost. And you have to do some things when you're doing that. That is, you can include the stormwater runoff. So the infrastructure that exists right now, you can't just up the density without affecting the infrastructure. So you have to put in what are called green stormwater infrastructure. So that's what you see in the courtyards that are actually holding water. The current runoff on the site we're holding that water for 48 hours and then releasing it slowly so you don't create more flooding within the site. And we're also using that to change the solar heated air adjacent to the building by using evaporative cooling on the outside of the building adjacent to the building, which we can reduce the temperature some 8 to 13 degrees Fahrenheit by using rain gardens adjacent to the building. We also are collecting harvesting the rainwater from the PV panels on the roof of the building and from the galvanum roofs of the building, and we're storing it in water bladders. So we don't have these big cisterns on the site, and the water bladders are in the 2-foot crawl space under the building. Because we're building these buildings off-site and we're bringing them onto the site. The concrete slabs have a tremendous amount of embodied energy, so we only have a concrete perimeter beam with a 2-foot crawl space under that. So that reduces the amount of concrete and steel that we have in that particular beam, and that becomes a place for our water. So we're able to use all of the water that we're collecting. We're not using it for drinking purposes or any potable water sources, which is illegal in Austin right now. What we're doing is using it for irrigation primarily. So we're able to keep all of the rain gardens and all of the landscape water, which is our biggest use of water in Austin, is irrigation. And so we were able to reduce that particular water use. We were able to add this roof deck on the 3rd floor above the ADA units, which has an outdoor kitchen. And as you can see in this, the whole trick to this, of course, is when you're looking at zero net energy, is like you're collecting much more energy during the day, and then you're running your meter backwards on net metering, and then you're pulling that energy back out at night. Because again, these are sort of like the big use of this one is not during the day. It's really a big nighttime use. We're actually dropping the EUI, the energy use intensity of the building, through the passive house kind of thing to make that happen. And so we ended up writing a new code for the transition zones within the neighborhood. So hopefully we can make that compatible. And what we begin to see is if that happens everywhere across the city, Yes, we can make the 100,000 new homes. But we have to do it in big numbers to be able to do that. And if we do that, we can reduce your per capita footprint from, as I said, 10.8 down to 5.6 by 2030. That's sort of a pathway to that. And the last thing I'll show you is what we're doing right now. So this is our latest solar decathlon challenge. And so we're taking on student housing. That's again about 20% of that 100,000 units that we need to build. It's going to be student housing. And so by building new dorms, we can get free up a lot of affordable housing, a lot of apartments in Austin for other folks. And so Austin we haven't been building new dorms in a long, long time, but we are now. We just finished the new graduate student dorm on East Campus. We're building a new one right over here by the Presbyterian Cemetery. And so we just bought W Mall. So we're slowly adding a lot more. So to do that, we were working with the Blackland neighborhood and terrace the building back down. This is the sort of proposal that the students did. And it's all based on, this is for medical students. And the way that they do this is they sort of teach themselves almost. They form a team, a pod, and they have one doctor that works with that pod and one proctor that works with that pod. So it's a 24-hour deal. It's a co-op. So they have one kitchen, one laundry for that for the apartments that front this open courtyard, and they actually have classes in the dining room at night. The study hall. There's a clinic on the first floor. That's a people's clinic. That's free clinic for East Austin. Part of the nursing. This is the light well. Within that, the sort of, again, the exterior wall in this that we're doing passive house stuff to it. So here you can see again, that's sort of like that envelope where we're getting it our EUI from 55 down to 2. On the prefabrication of how these particular projects will be built. We actually get into costs. So we're looking at about $161 a square foot, which is about $40 a square foot cheaper than what they built. They do graduate student housing for. And we're going to add to that about $12 a square foot for the new energy conservation features and water conservation features. Just to say that, we're going to be pretty much zero on an annual basis. We're going to use the rainwater for flushing the water closets, which is a big 30,000 gallons a month. The HVAC system is this new mechanical idea where there's no outdoor unit. It's all done with an ERV and a air source heat pump working together. So we have a 6,000 BTUH in each one of these particular units. It's the lighting load and the actual, to get the PVs on it, we needed almost 12,000 square feet of PV panels. And so that's what the west wall of which would be looking at the women's softball stadium. And we have resiliency in water and resiliency in power, which we have to have for the cleaning. And just to finish with this, this is sort of like the bottom line of what we're coming to. So you see in yellow here, that's the embodied energy, the energy required to build the materials to build the project. So there's an initial big hit, something in the neighborhood around 400 kilograms per of CO2 per square foot per meter squared. That's just the initial one. Whereas what you're seeing in red would be the benchmark. That's sort of like, again, code. What you see in the blue below that would be Zero Net Energy Ready. And we're doing even one that's a passive house, which is the dark one. So if we can do that, we have another upgrade of maintenance in 15 years, because using these DX units, we have to replace them all in 15 years. And in 30 years, we're going to have to replace all the windows because there's going to be obsolete technology. We're going to have to replace all the HVAC. All of that has to be replaced. So that's all adds to the embodied energy. So between now and 2050, half of the energy that we're going to use is embodied energy, not just operational energy. So we had to like absorb that cost into it as well to be able to get to zero net energy by 2050. And that's an ambitious goal, but it's possible and preferable. Okay, thank you.
Got one question online, anything in the room first? No one, a fire hose of understanding systems of buildings, water, energy, heating, cooling, so that's quite the fire hose of information. But a question from the from online here kind of relates to I guess it's about remote working. How do we think about the remote working in terms of the energy meeting your energy goals as you said? So shift to remote working and the need to localize more jobs, is there opportunity to develop new integrated technologies into buildings to enhance sense of adjacency and more structures and a multi-location office model? 20th century office location model is ripe for redesign. So any thoughts on that office buildings working?
Yeah, I think you know, if you want to really make a difference in the building, it's the envelope. You know, I think we're going to see new envelopes. You know, mid-century, 20th century building envelopes in New York City were single pane glass. They were hermetically sealed. You look at the new Bank of America building. It's got you know, double envelopes, vented. It's got variegated frits. It's got S floors and return airs that and displacement air conditioning. You know, it's just completely different. And so I think there's really great opportunities to see the sort of new ideas in building technology. I was asked one time, it's like, okay, with all these new technologies, you know, are you going to change all the windows out in 30 years? Yeah, we are. Because this is going to be obsolete. So how do you not design something that's obsolete? And I would just say, just look at your laptop. How do we make them keep up? Well, I'll send you new software. So as buildings become smarter, so I'm not thinking about maybe one thermostat in a building. How about 2,000 thermostats within a building with different actuators and sensors, so that I can constantly be upgrading that building technology. So as buildings become smarter, we get better envelope designs. We haven't seen anything yet. The new stuff is going to be completely different than the kind of 20th century stuff that we're building.
What do you use to do the energy models of these homes? Do you use Energy Plus, or like I'm just wondering what software you're using.
We've used a series of ones. First of all, we use ASHRAE 90 to do our by hand calculations. Then we use Ecotech, and then we used Open Studio.
Okay.
And I think Open Studio replaces Energy Plus.
I think it's all been integrated into Open Studio now. Yeah. Okay.
Yeah.
Cool. Thank you.
So I that's the software that they're using into it. I'm not a big software guy, so.
Yeah, other hardware spaces, there's this movement toward the right to repair being pushed over in Europe mostly. I'm curious if that concept exists in housing and modular and component-based housing. I think you were speaking a little bit to that around the HVAC systems.
I'm sorry, I'm old, so I'm gonna have to get you to relay that.
Yeah, he's sort of talking on some technologies. A right to repair is an issue for some technologies, and if you get more modular in the homes, do you anticipate or are you seeing any kind of issue with right to repair things in your home if you make it more smart or something like this?
And upgrades to adapt to future technology where we're not having to change just 10% change.
Well, the only way I know how to do it is just, again, to make the building smarter. You know, so everything's gonna be energy management. And then I can actually upgrade that software, which would make the building, you know, at least perform better, to keep up with it, instead of having to change out a whole new system. You know, when we find our laptop, obsolete, doesn't have enough memory or whatever, we don't open it up and take the motherboard out. Good. Because the shell is still good. So you gotta think about that the same way we do buildings, like the structure of the building, because we're using a lot of heavy timber now, is gonna last 300 years. The facade may be 60 years, 60 to 80 years. We have buildings on this campus that are 100 years old, or longer, that, you know, because they built the facade to last, to be able to last. But we tore down the engineering science building to build the EEB building, because the technology of that building was just so obsolete. You couldn't adjust it to the new kinds of labs. So there is a lifetime of buildings now based on technology where you do have to change the whole cover. You have to change the whole package to do that. And I just would say that we're looking at technology now, maybe that, like our equipment maybe has a 15-year lifetime or 25-year lifetime, before we're starting to think about, we need to upgrade that in with it. The PV panels are only last 25 years. So by that time, we'll be looking at efficiencies that are about 30% for sure.
So I suppose one of the more difficult retrofits of building components. So you mentioned windows. It sounds maybe quite intrusive. I mean, do we see a lot of what goes in? Some, for example, a window, rebuilding a window, you have to take out the whole frames. It's depending on the design. Do we have the right designs to retrofit windows over time?
Yeah, there's a whole bunch of people making a lot of money replacing windows in Austin, you know, upgrading them. But I think from what I can see, the new windows, the new ideas are it seems to be that the window could be an energy generator. So there's LED windows that can change, you know, its shading coefficient as it needs to be. And I'm looking at some research that's going on that I don't know if you've been on a new Dreamliner, for instance, but the windows in the Dreamliner, you no longer have to pull the shades down when you're down, because it does it automatically, because the window is changing its opacity depending upon what the weather is outside. So some of the new LED windows where you do stuff like if the sun moves across the window and down, the shading device moves across the window like that. So what we're looking at right now is just really crude technology compared to the ability to what we see in nature. For instance, we'll look at more mean radiant cooling systems. You look at your own skin, for instance. If it's too hot or too much sun, you start getting a suntan. So it begins to self-regulate, or you get freckles, or your blood vessel dilate, or you get the shivers, or you get other things. These are the kinds of biophilia devices that we're probably beginning to see happening with our engineering technology that's going to make windows go through the same revolution that lighting did when we went from incandescent to fluorescent to now LED, which used to be expensive, right? Too expensive. Now they're not. And they're so much more energy efficient that office buildings are now skin dominated, where they used to be interior load dominated. So, you know, I can't anticipate technology except to tell you that it's coming, and it's happening faster than we think. But so is climate change. And I'm not so sure it's just a technological fix.
So who did we contact? There's a project, master plan community, East Austin. The land is ready to start for an active living community, which is a zero net energy consumption. Contact you or someone else. Is ready to start project.
Well, like I said, we need 100,000 units. So all of New York Probably has about 14,000 people. So what do I need?
We can do 100 units and it's 50 acres available, ready to start with water, electricity and sewer.
It is probably, and you know, especially if we eventually move towards some kind of fusion, then you don't have to do it on a central basis, you can do it on a neighborhood basis. Which probably makes a lot of sense towards the second part of this. That will start beginning to see that, I would assume. But you know, we're moving from a centralized system to a distributed system. Right now, and you know, we have to do some things about wheeling power, you know, within a neighborhood. All of those, you know, things that have to change some laws. But it's all coming.
All right, so let's end it there. So thank you again, Michael Garrison.